Welcome to my new calculus channel. I am John Gabriel. In this video I'm going to talk about the joke that is commonly referred to as the real numbers. Actually it's more than just a joke, it's really a tragedy. It's a tragedy because real numbers don't actually exist. And why, you may ask, do real numbers not exist? Well, in mainstream mathematics, real numbers are defined as a set that contains the irrational numbers. Now, the irrational numbers do not exist. Okay, so I know most of you have grown up being taught that things like pi, square root 2, e, etc. Are all irrational numbers. That's actually untrue. They are all incommensurable magnitudes. Okay, a magnitude is only the idea of size, extent, dimension. It's not a number. If you watch my YouTube videos, you will see a video dedicated to the derivation, the Euclidean derivation of number. And you will see in that video that there is a definition of magnitude long before the definition of number. In fact, the ancient Greeks never thought of magnitudes as numbers, but numbers were eventually derived after magnitudes were established. So the very first ratio was actually a ratio of magnitudes. Okay, so whatever this ratio was, and it wasn't written like that actually, it was written like this. If we had any two magnitudes, whether they were length or mass or volume or anything, let's just use length for this example here. If we had any two length magnitudes like this, then a ratio of magnitude would simply be alpha vita and gamma delta, or CD in English. Okay, so this here is a ratio of magnitudes. Incidentally, if you wanted to write that in Greek, it's alpha vita. Whoops, what's happening there? My pen's gone. Alpha vita gamma delta. Those are the small letters. Okay, enough of that. Now, let's get back to the topic. So, incommensurable magnitudes are not numbers. Okay, they're not numbers. What does incommensurable mean? What does incommensurable mean? It means that none of these numbers here, or many other numbers, can be measured in terms of the unit, okay, or parts of it. That is, you cannot find an equivalent fraction in any radix that will give you these numbers. That's because they're not rational numbers, and the only numbers are rational numbers. There are no other numbers. I don't care what your professor told you at university, he's an absolute moron, because he's never understood. In fact, most professors have never understood what is a number, or mathematics educators. So I'm telling you the truth. And yes, I know the truth is contrary to most of the stupid people that live on this planet. But I happen to be one of the very few intelligent people. That's not arrogance, that's just a fact. And I'm telling you how it is with facts. It's not that I haven't studied mainstream mathematics. I've done all the advanced courses in mathematics. Real analysis, advanced calculus, metric spaces. I've done everything there is to be done. I've even done group theory to a very advanced stage. So there's nobody out there who's going to look down on me and tell me that I don't know what I'm talking about. I do. And there are other professors of mathematics who agree with me, even though they're in the minority. Well, I've always said that if I had $1 for every worthless mathematics dissertation ever written, I wouldn't be recording this YouTube video right now. In fact, I'd be a multimillionaire. Most people on the planet are unbelievably stupid. Now, coming back to this issue of equivalent fractions. So, what are equivalent fractions? Let's think about that for a second. If you have a half is equal to 2/4, these are called equivalent fractions. By the way, there happens to be one instance where these two are not equal. Can you think about that for a second? Well, let me help you. What does this bottom part here mean? It means if we have a unit, it's divided into two pieces, doesn't it? And this bottom part here, the 4, means if we have a unit, it's divided into 4 equal pieces. So the only time these fractions here are not equal is if the unit that we're using is not the same. So for example, if the unit in the case of this fraction here is this big, and the unit in the case of that fraction is that big, then 2/4 is not the same as 1/2. Okay? Does that make sense? Because here you have 2/4 like that, and 1/2 is this. And clearly, this shaded area is not the same as that shaded area. So the only instance where equivalent fractions are not equal is when the standard of measurement, that is the unit, is not the same, as I've shown over here. Okay, so now that out of the way, what happens when we convert, and I've gone over this just very briefly in the derivation of number, the Euclidean derivation of number, what happens when we convert a fraction such as this into an equivalent fraction in some radix system? What it means is that we can actually write this number with some factor of 10 at the bottom here and digits at the top. Okay, that's what it means. So for example, if you get some idiot professor telling you that 1/9 is equal to 0.11111, that's absolute rubbish. Or that 1/3 is equal to 0.33333, that's also absolute rubbish, because there is no way for you to write this in this format over here. Okay? There's no way for you to write this in this particular format here. But we can write a half that way. We can write a half as 5/10. And the way we do that is not, incidentally, not by long division. We do not use long division when we convert proper fractions into a radix system. So for example, we have the base 10 radix system here with the radix here, 10 to the minus 1, 10 to the minus 2, etc., 10 to the 1, ... We want to see what to write over here to represent a half. Well, we're just going to write a 5 there, because all we need are 5/10. Yes, 5's cancel out, and we got a half. How do we get a half? Well, we say a half times 10/10, which is the same as 1, isn't it? Is 10/2 times 1/10, which is 5 times 1/10. And that makes sense, because this is what this means. Now notice, you don't actually even need 0 in number systems. It's only there for disambiguation. For example, if we didn't carry this template around, this radix template, and we just wrote 5, nobody would know whether we meant 0.5 or 5,000 or 0.0005 or anything else, right? And this here is the same as 5/10,000. So an equivalent fraction must have that radix system with the factor of the radix system in the denominator. And I know you've seen this sort of thing happen before, where you say x is equal to 0.333 like that, and you say 10x is equal to 3.333, etc., and that gives you 9x is equal to 3, so x is equal to 1/3. Okay, but 1/3 is not expressed in terms of a factor of 10. So what you'd really need is just something like this, and some digits up here, which will give you 1/3. It's actually impossible to do that, by the way. It's impossible to do this. There is no way to find an equivalent fraction in base 10. I mean, you may say, oh well, okay, what about this? You could do this, by the way. I was the first to come up with this, but I'll show this to you. You could say k equals 1 to n of 3/10 to the k plus 1/3 times 1 over 10 to the n, right? Okay, so you could express a third this way, but if you just chose a value for n, let's say 2, then you'd have 33 over 100 plus 1/3 times 1 over 100, and that evaluates to 33 over 100 plus 1 over 300. But already you know that's not going to work out, because this here cannot be expressed as 10 to the power of some integer. See, there's no way to express 300 as 10 to the power of some integer. And I don't mean 3 times 10 squared. That's wrong. It has to just be 10 to the n, okay? That is an equivalent fraction in base 10. Alright, so now that I've got that out of the way, I'd like to go back to the story about real numbers. There is no valid construction of real numbers. Now, I've written extensively on that. I have an article. I have plenty of comments at Start2, heated debates and comments. And I've also written an article on LinkedIn called How We Got Numbers. I'll provide the links to all these pages at the end of the YouTube video. And in these articles, I explain how Dedekind constructions and Cauchy sequences are actually rubbish, and they don't produce real numbers or irrational numbers. They're actually a joke. And one thing I'd like to focus on very quickly right now is that if you look at the construction of numbers in mathematics, they define a number as the limit of, actually they define a number as an equivalent Cauchy sequence or Cauchy sequence, but every Cauchy sequence has a limit, so I think I'm free to say that a number is equal to the limit of some equivalent Cauchy sequence. In the case of a quarter, the limit is the sum, okay? So how does that work out? In the case of a quarter, let's just clear this all the way here. In the case of a quarter, the limit is the sum. So how does that work? A quarter, is equal to 2/10 plus 5/100, which is equal to 25/100. Okay, so in this case here, the limit of this series is the sum. That's true. In the case of a third, so let's go back to the case of a third. So if we have a third here, that's 3/10 plus 3/100 plus 3,000 plus ... In this case here, a third is not equal to the actual sum. It's equal to the limit of the series as n goes to infinity, right? And so a third is not actually equal to the sum, but the limit. And this is due to the idiotic definition of Euler, the mathematician Euler. Euler defined the sum to be equal to the limit of the sum in this case, okay? And in this case here, mathematicians define the fraction to be equal to the sum. So the sum equals to the sum. So we've got the sum equal to the sum here. Here we've got the sum equal to the limit of the sum. And finally, in the last case, in the case of square root 2 or pi or anything else, nobody has a clue what the limit is, because it could be some symbol or its partial sums. So if you look at a number like pi, you know, nobody knows what the limit is. You can't write 3.14159 ... and say that's pi. That's absolute rubbish. Also, you have to bear in mind that whatever the limit here is not a number. Whatever this limit here is, actually let's call it L, to this particular. So if you have a sequence, a Cauchy sequence of pi, you would write 3.13.14 ... Okay, so this thing here supposedly has a limit, but it hasn't been established that this limit is a number. It hasn't been established. If it's not a rational number, then what on earth is it? Okay, we haven't established. We're trying to establish irrational numbers. You can't say that this limit is a number when you haven't established that it is a number. And in this particular case here, we haven't. And it's very dumb, it's very idiotic to say that this here is the real number. Because if this here is a real number, well, it really tells us nothing. It just says that this supposedly unique representation represents pi. But if this is the case, then pi must be rational, because if we just add all these different terms up, it's always going to be rational. Yes? So obviously, whatever the fools in modern academia are talking about, they're not talking about a number. They're talking about some ethereal limit, okay? In other words, nonsense. Okay, so in the third case here, rule 3 that they have, so they have 3 rules for numbers, is particularly amusing because it assumes the completed infinite radix representation is possible. This is the last paragraph here, okay? Mathematicians define the number by this myth. Interesting to note is that if one accepted the infinite unique representation, then whatever is a limit, it is not equal to the completed infinite representation. Because if it were, then guess what? All irrational numbers would be rational. Ha 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 ha. What a joke. An absolute joke. Can you get anyone more stupid than modern academia? I doubt it. Alright. Now, before I finish off, I have maybe 2 or 3 things to go over. First of all, I'd like you to realize that the ratio 0:0 is a ratio of magnitudes, and because the Greeks didn't have magnitudes, they didn't care about 0. But if you read this comment of mine here at Statu, and I do provide a link in YouTube, I will provide a link, you will see that limit theory has no place in mathematics, and that rather than writing this rubbish here, down here where I'm pointing my cursor, it could be written this way. Because x:x is not the same as x divided by x. I'd really leave you to read this comment to understand for yourself exactly what's going on. If you have any questions, you can always go to the articles that I recommended. Okay, and then there are other academics who agree with me. Professor Wildberger is one of them. Professor Mukenheim is another. This here is an excellent link from Wildberger, which I will also provide in the YouTube comment section. But it's a paper he wrote about set theory and what you should believe. And it's absolutely spot on. It's essential that you understand what Wildberger writes here, because it goes right to the crux of the matter and exposes the foundations of mathematics, which is a lot of rot, and also real numbers, and it goes into quite a few details why the modern construction is not really valid. Another article that appeared not so long ago in the news was one by Wired.com, and it said, "Will computers redefine the roots of math?" And it's interesting because it actually shows that the more complexity we have in set theory, the harder it is to write anything that is flaw-free. So what we have here is a good reason to believe that a lot of the PhD dissertations, which are on either set theory or some kind of topology or some other shit, excuse my language, are actually very difficult to accept as fact, because they're based on such complex axioms, such complex mathematics, such religion in mathematics, that it's impossible for any of them to be without flaw. I also heard not so long ago in the news that a computer-generated program found a lot of these papers were actually plagiarisms of older papers. This mathematician, Vygotsky, was actually a Fields Medal winner in 2002, I think. And so, okay, those are 2 articles over there that you can read. And finally, I'd like to go back to how we got decimals. Okay, so according to history, Simon Steven was a little bit of a dimwit. He was a Dutch arithmetician, engineer. Who cares? Don't really care too much about what he did. But Steven must have played around with, some monkey business with decimal arithmetic, because you actually wrote a paper on decimal arithmetic. Let me just write this down here. 170 is equal to 0.142 857. Okay, 857. All right. Now, a lot of people will look at this and say, well, that really represents 17. It doesn't represent 17. This representation here is a symptom of a rational number when one attempts to express it in a base that does not contain all the prime factors of the denominator. Okay, that actually happens to be a theorem. For the life of me, I don't understand how morons can still insist on this rubbish when the theorem states clearly that unless a particular proper fraction, where q is a denominator, has all the prime factors of q in a base b, it's not possible to express this in the radix b. Okay, so let me restate that. Unless b contains all the prime factors of q, then it's not possible. It's not possible to find an equivalent fraction in base b. Okay, this is the moron who started decimal representation. Steven also put together certain rules whereby you could multiply numbers like 3, 5, 6.28 by 2, 3.1, like that, and also how you could divide and do lots of other things without ever understanding what on earth is a fraction. Okay, so you could do all the 4 operations of arithmetic: multiplication, division, subtraction, and addition, without understanding what is a fraction using Steven's paper. Okay, so the word for mathematics in Dutch or Afrikaans is wiskunde. Wiskunde is a calque, actually, because it comes from a Latin phrase which means knowledge of that which is certain. I think it's one of the few languages which do not directly borrow from the word mathematics from the Greeks. Chinese is another one. In Chinese, the way mathematics is pronounced is shushue. Now, shushue literally means number learning. Okay, number learning. So it's also a calque. Now, coming back to this 17, let me just clear some space up here again. Oh, come on. Right. Now, go away. Right. So now, over here, we have this. We could write this as an equality. For example, we could write 1, 4, 2, 8, 5, 7 like that over, how many is it? Thousands, 10,000s, 100,000s, millions. So we could write that like that, plus 17 times 1 over 10 to the 6, right? Okay, so you could write 17 like that. If you had 2 sevens, then that would be 2, whatever the first recurring or repeating part is here, and a 2 here, and the rest would stay exactly the same. So this is 1/7, okay? Now, the problem here, you might say, is, well, doesn't this express it as an equivalent fraction? No, because over here you have 1 over 7 million. And it's impossible to find an n here such that this is equal to that, okay? It's impossible to find an n, an integer n. Let me repeat that. It is impossible to find an integer n such that this is equal to 1 over 7 million, which means you cannot find an equivalent fraction for 17 in base 10, because 10 contains none of the prime factors of 7, which are 1, well, actually, which are just 7. So 10 does not contain any of the prime factors of 7, and so it cannot be expressed in decimal. Okay, I think I've pretty much covered everything, and I would like to also tell you about my Google Drive over here. I have made Applets, articles, 10 lesson course, and NC Applets available to you, so you can actually go and read those articles, and I will provide links to those folders in my drive, and you can look up that data if you're interested in it too. And so I hope that you have enjoyed this presentation. Also ask you to visit my new calculus site. It's the first and only rigorous formulation of calculus in human history, and I hope you enjoy studying it. Also, I hope you've enjoyed this presentation. This is the New Calculus channel, and I am John Gabriel. Till next time.